This lesson is an introduction to function transformations. Yesterday we did a discovery activity on Desmos where we looked at functions and how they are transformed on a graph and how it impacts the equation of that particular function. The generic notation for that is if you have a y equation and we can say that we have some sort of a stretch or shrink factor in the front of the function, and then we would say the generic function could be represented with f of x, but what we would also include is some sort of a transformation value. A horizontal transformation would be contained in parentheses with the x, and the minus is part of the equation, and this indicates the h value whether it moves left or right. Now the plus k on the back indicates a vertical shift moving up or down. So when I look at these functions in terms of each different family, the simplest function in two of the families are what we're going to talk about today. So the first function here, y equals x squared, is the quadratic equation. And the quadratic function, the most basic function, or the parent of all quadratics, is x squared. And the other one we're going to be looking at is the absolute value function, and this is the parent, the absolute value of x. Notice both of these only have x values in them, and then the actual operation, for example, here squared, and this one is absolute value. So when we have a parent function, the a value is a 1 for the parent only, and the h value, if I just want to have x in parentheses and no h has to be 0. And then, of course, for the parent function, there's nothing added or subtracted on the back. So the k value is 0 as well. The values for a, h, and k represent potential transformations to the parent function f of x. These are possible values that we can add, subtract, multiply, and or divide. Although it is transformed, it will still retain the characteristic qualities of its parent function. So the quadratic function, like we mentioned above, the parent function is f of x equals x squared. If we add in the a, the h, and the k, you'll see that you've got x minus h in parentheses, quantity squared, the plus k is added onto the back, and then the a value, which is a coefficient up front. And the hk value, when you graph a quadratic, it takes on a U shape. And the parent will look something like this. And later on, when you get into Algebra 2, they'll talk about the fact that this is your vertex value. And that is your hk value from your generic equation of your parent function. So this h and this k indicate the vertex. Now let's talk about what each of these variables or each of these values do to change your quadratic function and your absolute value function. So obviously a, h, and k are going to be replaced with numerical values. So let's talk first about what that a does. So a is a stretch or compression factor. It's also potentially a reflection factor. So when I speak about that, I'm talking about, for example, if I had something like negative 2x squared. This negative is going to cause this to flip over the x-axis like we saw in the Desmos activity yesterday, and that too is a stretch factor, so it causes the y values to double in size. So you can add this into the notes that the a, if it's negative, will flip or reflect over or in the x-axis. And if the value is larger than 1, the a value, ignoring the negative in front, if just the a value itself is bigger than 1, you have a stretch factor, so it makes the object look taller quickly. Or if it's less than 1, in other words, if it's between 0 and 1, for example, like a half, it'll make the object compress. It'll look shorter and wider. The h value. Notice that in the parent function for the quadratic, the h value is located in the parenthesis with the x. And remember that minus sign is part of that formula, so the h value indicates whether it moves left or right, but you have to think about it being the opposite of what you actually see in terms of sign. So that h value is a shift that shifts the parent function horizontally left or right. The k value is added or subtracted to the back of the parent function, and it causes a shift of values that shifts it vertically up or down. At the top of the second page, we have some practice problems. Part 1, describe the transformations that happened to the parent function that's a quadratic here. So what they want you to do is look at the values for a, h, and k in terms of whether they're inside, outside, or multiply with the function. Also, you should check to see if the a value is negative. So number 1, f of x equals negative 2x squared plus 6. I can think about this in terms of rewriting it with h and k. I notice that the x value doesn't have anything added or subtracted to it before it's squared. So I could replace that with an x minus 0. And of course the plus 6 is on the back. So to describe the transformations for this, it's reflected in the x-axis because I see this negative is flipping. Then I have this stretch factor of 2. The y values will grow at twice the size. I don't have any kind of a horizontal shift. I'm not moving side to side because of the 0, but I do have a plus 6 on the back, so it's going to take the entire function and shift it up 6 units. Go ahead and try to do 2 through 5 on your own. Pause the video, and when you finish, unpause and check your answers. Go ahead and check your answers for 2 through 5. The one thing I do want to make you notice in number 3 is this x plus 8. If I rewrite it with the minus that's in the formula, that's really x minus negative 8, and that kind of clarifies which direction that function is moving when you move the parent function. Given the parent function f of x equals x squared, write the function rule for g sub x after the given transformation. Match the description with the correct equation in the box. There are more equations than there are descriptions. Go ahead and answer numbers 10 through 17. Pause the video while you're working, and when you've finished, unpause and check your answers. Check your answers to numbers 10 through 17. Part 2. Consider the original absolute value function defined as f of x equals absolute value x. Find the values needed for a, h, and k. Let's do example A together. So this says take the parent function and shift it 5 units to the right. There is no vertical shift, so this back value would be 0. There is no stretching or shrinking of the function. There's no flipping, so that value in front, which is the a value, is a 1. Moving 5 units to the right, that's in the positive direction, and so we put a 5 in that position. Notice the minus is part of the original equation for the function. Go ahead and finish B through E on your own, so pause the video. When you finish, unpause and check your answers. Here are the answers for part 2. Go ahead and check, and if you have any questions, make sure to ask a neighbor or the teacher. Part 3, parent function graphs. So we're going to look at the different characteristics of each type of parent function for the quadratics and the absolute value. This first picture is of the parent function y equals x squared. And so we're going to look at different values like domain and range and the vertex. Now the domain is an indication of what are the restrictions on the x values. So when I look at the equation for this, think about the fact, are there any values that I could not put in for x which would result in no output or no y value answer? And there are none of values like that. There's nothing that you could consider. So what we're going to do then is go ahead and write the domain in what's called set notation. And that means that all my answers are possible. So if you want to, for now, you can write all real numbers or you can write a capital R. That indicates all real numbers. When you get into Algebra 2 Intensified, you'll be able to see this written as negative infinity to positive infinity. This is known as set notation. Now the range of this function, that's the y values. What I'm going to do is I'm going to run a horizontal line through my vertex. That is the very bottom of this function. And that point there, that vertex is 0, 0. All of the y values are above that line. So that means that all of my y values are greater than or equal to 0. Now you can write it in that format, or when you get into Algebra 2 Intensified in set notation, that's from 0 to infinity. But for now, you're welcome to write it as just y greater than or equal to 0. The vertex I've already discussed. That is 0, 0. And key points, I've got two things here. I have a table on the right, and I wanted to list the axis of symmetry. Now, the axis of symmetry is that line where you have a reflection running from left to right. So I'm going to go ahead and put in my axis of symmetry, which is a dotted vertical line. And I'm going to write that equation, which is x equals 0. And that shows that from left to right, that this line creates a line of reflection. So the left and right sides look identical. Now, table of values for this. What I like to do for a quadratic is list 5 key points. And you can add this table onto your paper as well. Notice that I have the vertex in the center at 0, 0. Now, if you type this in your calculator, y equals x squared, you can look at the table of values. But it's very quick to do the parent function and its table for a quadratic. If I put in a 1 and I square it, I get 1. Of course, if I square the 2, I get 4. Notice that I've got the negative values first and all the way up to the positives. So what I see here is that my y values are symmetric, 4 and 4, 1 and 1 and 0. Let's go ahead and take a look at an equation that's been transformed of a quadratic. So I have the quantity x minus 3 all squared. I can rewrite that using the a value, the h, and the k. What that indicates to me is that I don't even have a vertical shift at all. I do have a horizontal shift of the parent function, and because it's minus 3, I'm only looking at that 3, so that's going to move 3 units to the right, and the 1 says there's no stretch or shrink factor. Now the hk values, those are the 3 and the 0 right here. So that is also my vertex. And this is going to help me do a very quick graph for this. Now moving left or right, this minus 3, the minus part of the formula, so that 3 means I'm moving 3 to the right. And I don't move up or down at all. Now I need to make a decision as to whether this particular function is an open U shape or does it open upside down. It would open upside down if it had a negative in the front, but in this case there's a positive coefficient, so I'm going to go ahead and put an up for that. Now you can draw both the parent and the original, if you or the parent function and the transformation. In terms of a rough sketch, the parent function kind of goes through here like this. And all I'm going to do is pick this up and move it over 3 units. So I really don't have to put that in there. Now next year your teacher may require you to draw both, but for now we can just go ahead and focus on the other one. So I'm only taking the vertex and moving it over 3 units to the right. And then I can use the points from the original and just plot those as well. So, and I want to go ahead and put in 5 of those values. It's kind of hard to see where these are going to be located, but this is the general location. So you're making that U shape. So the domain for this, that hasn't changed. There's no restrictions on that. And the range, if I do take a pencil or a line and run it across the bottom of this, everything's greater than or equal to 0. So you can put y greater than or equal to 0, or you can say 0 to positive infinity, like this. All right, draw in my axis of symmetry as well. Throw some arrows on the end. And that axis of symmetry has been moved over to 3, so that's x equals 3. Okay, number 2. Go ahead and look at the original parent function and see if you can compare it to this new transform function. See if you can fill in the vertex as well as whether it's moving left or right, up or down, and go ahead and graph it and see if you can do the domain and range. Pause the video and check when you're finished. Go ahead and check your answers. Notice that because this has a negative in front, it's going to be opening down, and we've taken the vertex and moved it down 2 units. So you can see over here I've got this graph where I've got a vertex at 0, -2, and it opens down. And of course you can use your calculator to find other points for this graph, and you can certainly plot them. There's going to be a point at 1, -2, and -1, -2, and then a few others as well. The domain doesn't change. It is all real numbers. There's no restrictions on what you can put in for the x value. But the range does change, because if I look at the vertex, everything is below negative 2 or equal to it. So y less than or equal to negative 2. And that's how you would write it for now. But later on, you'll learn it in set notation. Part 4. This is an absolute value function, and the parent function looks like this. It would be f of x equals the absolute value of x, like that. So the domain, there are no restrictions on what you can put in for your x value here. So your domain is all real numbers again. Now for the parent function, the range, if I put a vertical line, or sorry, a horizontal line at the vertex, everything's bigger than or equal to 0. So if you just want to write for now y greater than or equal to 0, that's fine. Your vertex is 0, 0. And key points here, if you did a table of values, I'd probably go ahead and put that vertex in the center. But what I'll notice is that the x and y values are identical for like 2, 2, 3, 3, 4, 4. And then in the negative side, it's negative 2, 2, negative 1, 1, vertex 0, 0, 1, 1, and 2, 2. All right, let's go ahead and take a look at a practice problem here. So for this one here, if I rewrite this, we have f of x equals negative x plus 6 plus 0. Vertex, remember this is your hk value. The h value is negative 6. It's going to be the opposite of what you see there. So negative 6 comma 0. And left and right, well, this plus 6 means I'm moving 6 in the opposite direction. So I'm going to move 6 units left. So 6 left. And I'm not moving it up or down at all. But I am going to flip this over because it is negative. So you're going to flip. And if I go ahead and do a graph of this, flipping this over and also moving it 6 left. So 1, 2, 3, 4, 5, 6. Hopefully I'm not too far off here. Right there. And I can actually use the slope on each side to kind of help me. So I'm going down 1 over 1, down 1 over 1. And same thing on the other side, down 1, back 1, down 1, back 1. It also has an axis of symmetry that you could use to reflect the points over and draw a very accurate graph. So I'm freehanding this, so it might not be quite perfect, but that's generally where it's located. So your domain for this is all real numbers. Now your range, if you put your pencil horizontally at the vertex, everything is below the x-axis. So your range is less than or equal to 0. Just a brief summary. So if you have x plus h in here, you're actually going to be moving h units to the left because it's going to be the opposite of what you see in terms of sign. X minus h means you're going to move h units to the right. K shifts. If it's positive, you're going to move up k units. And if it's negative, you're going to move down k units. Like that. And for this one, if you have a value being multiplied to the function, as long as it's bigger than 1, you're going to have a stretch. And of course, if it's a fraction between 0 and 1, you're going to have a compression or a shrink. We'll write both of those words there. Compression or shrink. We'll put that in parentheses like that. And when a is negative, you're going to have a reflection over the x-axis. Sometimes you'll see where people say in the x-axis or over the x-axis. Either set of wording is correct.